Okay, today we're talking about Chapter 9, Section 1. In, hmm. Oh, there we go. Introduction to Probability. Man, I hate how it just cuts that off. This is awful. But anyways, 9.1, an Introduction to Probability. All right, so we've come a long way in this course from learning how to multiply negative numbers to now going into probability. All right, so let's look at this. The terms related to probability. Put this on the page, and I think there's one more. Yeah. So random experiments. Okay, so there's gonna be a lot of snipping in this particular section because, well, there's I don't know. To me, I just feel like it seems like the best way to go about teaching this course, anyways. So terms related to probability. A trial is a repetition of the same procedure. Makes sense. An outcome is the outcome of a trial. Observed value of the variable we are measuring in the experiment. The sample space is a set of every potential outcome that could occur in one trial of an experiment, and an event is a set of outcomes. So these four terms need to be memorized. Yes, I'm sorry, but I mean, realistically, you pretty much know them, right? So random experiments. A random experiment is defined as an activity, as any activity or phenomenon that meets the following conditions. Okay, so again, there's a random experiment. There is one distinct outcome for each trial of the experiment. The outcome of the experiment is uncertain. The set of all distinct outcomes of the experiment can be specified and is called the sample space denoted by S. So let's look at tossing a coin. And again, I'm just gonna snip this whole thing. There's not much computation involved here. It's just really just, I mean, personally, I feel like it's just talking through it and just really kind of understanding what we're looking at, what we're reading. Alrighty, so if we toss a coin and observe the outcome, have we met the three conditions of a random experiment? Okay, now again, the random experiment was we have to have a distinct outcome. Let's just go back a second. I forgot them. Distinct outcome for each trial. The outcome of the experiment is uncertain. So a distinct outcome and an uncertain outcome. And then the set of all distinct outcomes of the experiment can be specified and is called the sample space, which we denote S. So looking here, uh, if we toss a coin, have we met the three conditions? All right. So since there can only be one outcome for each trial of the experiment, there will only be one outcome for each trial of the experiment, since it is not possible to observe both heads and tails. Makes sense, right? I mean, well, even if you landed on its side, you're not necessarily observing both head and tails, huh? All right. Two, obviously the outcome is unknown as you flip it, right? Unless of course you have a weighted coin, but we're not talking about that. Three, the sample space can be specified and contains two outcomes. The two outcomes are heads and tails. All right, since all three of these are satisfied, then yes, this is indeed a random experiment. Oh, here it is. Yeah, it is possible for a coin to land on its edge and thus neither heads nor tails. And in theory, however, involves a certain degree of idealization, which means in the case that landing on the edge will not be considered a possible outcome. Yeah, so the textbook has adequately what's one am I trying to say? Adequately planned for that particular student. It's like, but wait a minute, okay? Shoot, let's do this. Tossing a coin 3 times. Okay. Oh yeah, that's another thing is when we get to trees later on in this section, I don't have enough space to actually write them, so I'm just gonna snip those also. Alright, so toss a coin 3 times and observe the number of heads. Have we met the three conditions of a random experiment? Note, one trial of experiment is tossing a coin 3 times. All right, so um, it will obviously only there will only be one outcome, right? Heads or tails. Uh, the outcome is unknown, obviously, and then the sample space can be specified, and it's composed of 8 outcomes. Those 8 outcomes are the 8 possible outcomes you can have when you flip a coin 3 times. Tails, 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 heads, tails, head, tails, head, tail, tails, head, tail, head, 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 tail, and head, head, head. Whew, man, I did that pretty quick, huh? So of course, this experiment does indeed meet the condition of a random experiment. It has to be observed. These 3 steps have got to be observed for that to be the case. Alrighty, so rolling a dice. I'm sorry, rolling a die. Yes. All right, so here we go. Roll a die and observe the number of dots on the uppermost surface, right? The top, right? Have we met the three conditions of random experiment? Well, there's obviously only going to be one outcome. We do not know the outcome when we roll the dice or the die, and then the sample space, as we see, can be specified in the six outcomes: 1, 2, 3, 4, 5, and 6. And because of this, we do indeed meet the conditions of random experiment, right? So I mean, hopefully these examples are really driving home the point of what we're trying to do here, right? More stuff, and I guess I didn't necessarily have to snip this one, but I think it looks pretty cool with the playing cards there. Alrighty, so start from the top here. Assume we have a standard deck of playing cards consisting of 13 hearts, 13 clubs, 13 spades, and 13 diamonds. Draw a card from a well-shuffled deck and observe the suit of the card. Have we met the three conditions? Well, the first one, there will only be one outcome because we're drawing one card. Two, it is definitely unknown what we're drawing. And three, the sample space consists of the following set of outcomes: heart, club, spade, and diamond. So because of this, we do indeed meet the condition of random experiment. Right? So empirical probability, and I feel like I'm going really fast, and I know I am. I feel like this is one of those things that it's kind of self-explanatory and super easy once you're like, okay, yeah, we one outcome, it's random, and we can obviously show a set of what the outcomes can be. All right, next up though, we have empirical probability. So the word empirical uh, it means verifiable by observation. So empirical evidence means that we can look at it and then we can verify that this is indeed a true or false statement, or you know it could be a statement, it could be your engine's running, I don't know, just empirical probability. Uh, Thus, an empirical probability is a probability that is determined by observing a random experiment. Someone who wanted to determine the empirical probability of getting ahead on the toss of a coin would toss a coin many times and observe the number of times that head appeared. The probability would be computed as the number of times the head was observed divided by the number of times the coin was flipped. For example, if we toss a coin 3,000 times, that's horrible, and observed heads on 1,509 of those, then the empirical probability would be 1,509 divided by 3,000, which is obviously very close to 50-50, right? 50%. And then we have our formula, which again isn't too much of a brain buster, right? It's just the number of times we observe the event occurs divided by the number of times the experiment is performed. Of course, we see that here and here, and of course up here. So we're just going to make small little calculations here, calculations that I feel like are I hesitate to say this, but I feel like this is one of the easiest sections we went over in this course so far. But it is. I mean, it seems difficult, but it's not, right? So let's go ahead and begin. So example 5, calculating empirical probability. So a basketball player has made 300 of 420 free throw attempts. What is the empirical probability that the player will make a free throw attempt? Well, all you do is take the 300 and divide by 420, and you get 71%. Right? And of course, that is their free throw percentage. What is the probability he will not make a free throw? Well, if he has a 71.43% chance of making a free throw, I say he, sorry. If they have a 71.43% of making a free throw, then obviously, I take 100% and subtract 71%, and I get 28%. Now, well, 71.43. Now, the way that the textbook did it was they just divided it the other way. Well, not the other way, but the missed free throws divided by the free throws that were made, and you get 28%. I won't say I on the other hand, but instead what I would do is I would say 1 minus 0.7143, and of course that is going to be equal to 0.2857. So this is another way to go about getting B. So let's put B right here. And Either method's fine. I wouldn't say one is necessarily easier than the other because I feel like they're both pretty darn easy, right? Um, but yeah. Um, okay, so more snipping. Um, Again, I feel like it just looks way nicer. Hopefully you don't think I'm lazy doing this. You can definitely look at my other lectures and tell that I definitely do the computation when needed. I just feel like this is again just so easy, but I do feel like I'm taking shortcuts. Hopefully you don't feel that way. So a drug company is testing a new diet pill. 500 people participate in the research experiment. The results were as followed. So out of 500 people, 294 lost weight, 166 stayed the same, and 40 gained weight. That's me. If the drug is given to a patient, A, what is the empirical probability that the patient will lose weight? Well, the probability that somebody will lose weight, you take the lose weight, 294, and divide it by the 500, right here, 294 divided by 500, and you get 0.588, or 58.8%. Okay, so 58.8% of people will lose weight taking this diet pill. And I'll be honest with you, I don't think that's worth it. I mean, I don't like taking medicine and putting things into my body, but that's just me. B, the event, well, I'm sorry, B, what is the empirical probability the patient does not gain weight? Okay, so the probability that they do not gain weight, well, they're either going to lose weight or they're going to stay the same. So you do the lose weight and stay the same, you add those together, you get 460. And 460 divided by 500 is 92%, right, or 0.92. All right, so with taking this pill, there's a 92% chance that um, you will not gain weight, right? And again, I don't know, my own personal opinion. I don't think that's worth it. I don't think anything like that's worth it. Um, More calculating. Alrighty, so example 7 reads, a casino wanted to assess some new dice, so they rolled one of them 1,000 times and found the following frequencies of observation. That's a job I can do. Alright, so um, we have our number of outcomes here and the number of observations. Okay, this is 1, 2, 3, 4, 5, 6. This is obviously the sides of a die, right? Um, and you would think they would be, pretty even. And honestly, I mean, 1,000 times really isn't that many when we're rolling a die here. But calculate the empirical probability of each outcome. Well, what you do is you just take the number of each roll and then divide it by the total time, which is 1,000, right? So you'd say 160 divided by 1,000, or 16%, 14%, so on and so forth. You just you just take the number of observations and divide it by the total number of observations. And I guess that would be the hard part, huh? To figure out what is what. But I don't think you guys will be struggling too hard with that. I mean, you're in college. You obviously, got here for a reason. Next up, we have a classical approach. Let's see. Should I? Okay, we'll put this on the left side, and we'll put example 8 on the right side. Current page. All right, so classical approach. So the second approach commonly used in probability theory is the classical approach. This approach assumes the outcomes of the experiments are equally likely. Classical probability can be measured as a simple proportion, the number of outcomes that compose the event divided by the number of outcomes in the sample space, which is pretty much like what we did before, right? It's just the number of outcomes divided by the total number of outcomes in a sample space. So in example 3, a six-sided die was rolled. Let E be the event of observing a 5. What is P of E? Okay, so what is the probability of E if E is the event of observing a 5? Well, there's only 6 numbers, and so there's only one way to make a 5, so you say 1 divided by 6. Right? There's only a 16.7% chance that you'll roll a 5. Let E be the event of observing an even number. Okay, well, there, there are, again, 6 numbers, and half of them are even, so there'd be 50% chance, right? 2, 4, and 6 are even, 1, 3, 5 are odd, so I, I honestly am, I don't know. I don't know. I feel like that just it makes too much sense, right? Too much sense to be an example in a college math text. But that's that. So in example 4, right, we did our cards from a standard deck of cards consisting of 13 hearts, 13 clubs, 13 spades, 13 diamonds. Let E be the event of drawing a heart. Okay, well, if there are 13 of everything, right, and hearts make up 25% of the deck, and then obviously it's 13 out of 52 or 25%. Right, some more examples from what we did earlier. Example 2, a coin was tossed 3 times and the number of heads was observed. The sample space consists of 8 outcomes. We spoke of those 8 outcomes. Let E be the event of getting at least one head. Okay, well, looking at this, there are 8 outcomes, and how many of them have at least one head? Well, this one obviously has a head. This one 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 has a head. But tails does not have a head. So 7 of the 8 outcomes have a head in it. So you just simply do 7 out of 8, or 7/8, which is 87.5%. Hmm. And tree diagram. Don't don't necessarily know if it's needed, but we're gonna talk about a tree diagram, just because I mean it's going to be on the homework, obviously. But I'll be honest, I've never used a tree diagram beyond beyond this particular course. Now, I'm not saying it's not used, okay, and I probably shouldn't have said what I said, because I mean just because I don't use it doesn't mean it's not used. Okay. Yeah, so this was mainly the reason why I just wanted to snip a lot, and of course it's only one problem, but it is what it is. But it's the math is the exact same. You don't even need a tree for this. And what I mean by that is, well, let's look at the problem. So the problem reads, on your way home from work, you encounter 4 traffic lights. Assume the lights are equally likely to be green or red. We will assume there are no yellow lights. A, draw a tree diagram illustrating the possible outcomes of the experiment. And then, so here's the possible outcomes. All right, if your first light is only going to be green or red. Okay. Well, if it's green, you go to the second light. The second light's going to either be green or red. The third light is either going to be green or red from each branching off from there. And then we see our outcomes here. Okay. And this is just a tree, just kind of, green or red. Well, here are our outcomes. And it wants us to list these outcomes. And of course, just drawing a tree diagram, we're able to list these 16 outcomes. Right? And here's our sample space. There are a B, determine the probability of getting 4 red lights on your way home. And that all of us, right? Um, so if we have a red here, and then we go to the next light, we have a red here. We go to the next light, we have a red here. We go to the next light, we have a red here. Okay. There is only one outcome where I get nothing but red lights. Well, there are 16 total outcomes, but only one outcome where I can get a red light. Well, again, I just do 1 divided by 16, which is 0.0625 or 6.25%. And besides the rules of probability, that concludes probability. It's not, I don't know. I'm not going to say anything else. I think it's one of the simpler sections, especially being in the middle of a semester. I would be elated if I was a student because normally classes get a lot harder as you progress, but this one is a nice bone get thrown our way. Anyways, that concludes today's lecture.